onto branching and side branching. Here's a film of dendrites growing on a fiber. The branches on this first one have already sprouted, but you can see them grow, and they're growing. And you can see the side branches taking off. We noticed them a little ways back from the tip. This next one shows the two-level structure of the dendrite. We can just barely make it out on this case. Here's the top level. We'll have 3 branches, and here's the bottom level. The branches will sprout. Nakia's team back in the 30s took apart snow dendrites and discovered that they had 2 levels. But once the crystal gets big, you can't tell that there's a 2-level structure. And we'll show how this works later. First, how do the branches sprout? And why does the crystal look so symmetric? First, let's view the basic process. Now let's examine this process. Here's the initial stage, and all 8 faces appear completely flat. Now this is in the tabular regime, so let's look at a prism face up close. We'll look at this one, but the other 5 will be exactly the same. Layer nucleation occurs at a corner, where the supersaturation is highest. Now if conditions are perfectly uniform, it would happen at all 4 corners, but it doesn't matter, we can just focus on one. Now the nucleated layer will quickly spread around the perimeter, and they'll start moving inward like a constricting band. And focus on this cross-section, this dotted line. Here it's kind of blown up and exaggerated here. Here, this layer here, recently nucleated, it's in a region that's still in a high supersaturation, so it's moving relatively fast. This one, nucleated before, and it's in a region that has a little lower supersaturation, so it's moving slower. And as you go inward, they go slower and slower. As they slow down, they cluster together, like cars on a freeway entering fog. Now, this cross-section here is highly exaggerated. If we were to look at this, it would appear completely flat because these layers are so thin. But it doesn't stay this way. As the face gets larger, the clustering gets more severe, and a hole develops in the center. The hole grows. Because of the shape of the crystal, this hole breaches the prism edges first, dividing the crystal into a bottom level and a top level. Now, by this stage, if not from the beginning, the face here is fed by layers coming from this corner and that corner, but they cannot feed layers to this other level. So this other level is being fed by layers nucleating at these corners. Note also this cusp down here, where the crystal is a little bit thicker. As the face grows, this leaves behind a ridge or a spine that later we'll see as the source of the line going down the middle of the branch. As the crystal continues to grow, our layers coming in will then overcluster before reaching the center of the face. It happens on both sides, and it happens over here as well. So bingo, our little branches have sprouted. But notice that we'll often have 12 branches, not 6. But the top and bottom branches are very close at the beginning, and they compete for vapor. If a branch on one side, say the bottom, gets a little bit ahead, say because of some asymmetry, it then grabs most of the vapor, leaving very little for its twin. So the other level, this top level in this case, essentially stops growing. Now one asymmetry arises from the air rushing past the crystal as it falls. The crystals like this fall broadside to the air, so the bottom gets the fresh supply of vapor, and is then more likely to take off, as in this sketch. So in the end, we end up with 6 branches. And that's the origin of the 6 corners. Let's briefly review why this happened. Why are the 6 branches so nearly identical? Now, the initial prism arose from the honeycomb-like crystal lattice of regular ice, but that hexagon is not what we see. To have 6 corners, each branch must grow the same as the other 5. For this to happen, the prism face must grow by layer nucleation. As pointed out by Sir Charles Frank, no crystal could be so defect-ridden to have exactly the same growth rate by defects in all faces. Now look at our example. This face here is fed by layers nucleated at this point. The mirror face is fed by layers nucleation at the same point. It's the same point, it's layer nucleation, so it's the same rate. Similarly, along the side, those points are identical, and so they grow at the same rate, although it's a little slower. And here it is on a real crystal. Next, side branching.